The next thing we want to look at is a one-dimensional analysis of wind turbines. So we're certainly changing pace here from centrifugal pumps. The first thing is we're looking at a turbine rather than a pump. So this is a device designed to extract energy from the fluid rather than put energy in like a pump is. However, this is still an example of a turbo machine, so all of the principles that we've learned up to this point are going to be applied to this device as well. We'll just see how this analysis is done. First thing we want to do is take a look at a list of assumptions. So first of all, a steady state analysis is going to be done, same as we did with pumps. So we're not going to look at the case where it's speeding up or slowing down, just operating at steady state. Constant density, so incompressible fluid. It is air certainly, but the changes in pressure are small enough that we can ignore changes in density. Constant temperature assumption as well. Axial flow only. So this is a bit of a weak assumption for wind turbines, but it certainly gives us a good first approximation to the performance of a wind turbine. We're also going to make a uniform flow assumption, and that's kind of connected to the title of this, a one-dimensional analysis. So we're only looking at changes in velocity in the axial direction. We're not looking at any changes in velocity as we go away from the center of rotation of the turbine, so in the radial direction. So that amounts to a uniform flow assumption. We're also going to make a frictionless flow assumption, so we're ignoring the effects of viscosity in this analysis. And finally, no heat transfer. So these are certainly a large list of assumptions, but the idea here is to get at the essential performance parameter for a wind turbine and see what that looks like. So we're going to begin, as we do every control volume analysis, by identifying our control volume. So this is our little schematic of our wind turbine, and it's a horizontal axis wind turbine, but that isn't particularly important to this type of analysis. So we have however many blades we have in the rotor plane here, and then I've shown a tower. Of course, this is connected to the ground down here. The free stream velocity we're going to call V1. So this is the undisturbed air velocity approaching the wind turbine. The control volume that we're going to analyze here will look like this. So this is called a stream tube, and we introduced stream tubes back when we were first looking at the Bernoulli's equation. So the surface of this stream tube has no flow across it. So the surface of the stream tube is streamlines. So that's a surface in the flow with zero flow across it. Now you'll notice that the diameter of the stream tube at the rotor plane matches the rotor plane. So what we're looking at here is all of the air that goes through the rotor plane. This is called the rotor plane right here. So any air that goes through the rotor plane, we're interested in studying it. Now, as the air approaches the rotor plane, it's seeing this as an obstruction essentially, so it's slowing down. And we're going to study how much it slows down in quite a bit of detail here soon. So that means that the cross-sectional area of this stream tube has to be smaller here than it is here. We have our free stream velocity here, relatively high speed, and as it approaches this, it slows down, so the diameter of our stream tube has to get bigger. And it turns out that downstream of the rotor plane, it actually continues to slow down, so I've shown the diameter of our stream tube continuing to get larger. So this is the control volume that we're going to be looking at. Now we need to identify some axial locations along this flow. So one is going to be the inlet to our control volume, and there's a couple of intermediate locations that we're also interested in. Two is going to be immediately upstream of the rotor plane. 3 will be immediately downstream of the rotor plane. And then finally, location 4 is the exit of our stream tube, or the exit of our control volume that we've identified. So this is the control volume that we're going to use for our one-dimensional analysis. Now again, to come back to the word one-dimensional, we're looking at variations in velocity and pressure as we move in the axial direction. This is the axial direction. So that's the one-dimensional analysis. We're not looking at any variations in the radial direction. So that means that all of these velocity profiles at all of these locations are going to be uniform. No variation in this direction. They can change from one axial location to another, but they don't vary in the radial direction. So this is a one-dimensional analysis. If we wanted to do a more sophisticated job of this analysis, we would be allowing the velocities to vary in the radial direction as well. But that's the next level of sophistication. Now, the very first thing we're going to apply to this is conservation of mass. So we have an incompressible, steady flow here, which means that at any of these four locations, 1, 2, 3, 4, the mass flow rate is the same. Remember, this stream tube, there's no flow across this surface. So that means the mass flow rate at any of those four axial locations is the same. So the product of density, velocity, and area is constant. Notice the density, there's no subscript on it because it's not changing. But the velocity and area are both changing. You can see the area change in my little sketch. So this means there has to be a velocity change to go along with that. Relatively high velocity here, slows down here, and then it slows down even more here. So changes in velocity accompanied by changes in area. Other thing to realize here is that A2 equals A3. So 2 is immediately in front of the rotor plane, 3 is immediately behind, so there's no sudden area change in our stream tube. So A2 equals A3, and in fact that's the area of the rotor plane. So a very important geometric parameter of the wind turbine, essentially how big is it? What's the area of that rotor plane? So A2 equals A3, we're going to say. So that means that V2 has to equal V3. And remember, those are both axial velocities. So the velocity can't change through the rotor plane because the area doesn't change. Now we want to define a very important parameter in wind turbines, and that's the axial induction factor. So the term axial means that this is referring to the axial velocity, and induction factor is a way of measuring how much the air slows down as it approaches the wind turbine. Okay, so here's how it's defined. The axial induction factor, and we just use a lowercase a for that, is the difference in velocity from 1 to 2. So remember, 1 is the free stream velocity, so a long ways in front. That'd be a relatively high velocity. 2 is a reduced velocity immediately in front of the rotor plane. So that's how much the air velocity slows down as it comes to the rotor plane. And then this is turned into a non-dimensional number by dividing by V1. So the change in velocity over the velocity itself. So notice axial induction factor is a dimensionless number and it will not have any units. So another way to write this is that we can write V2 in terms of V1 and the axial induction factor. So just rearranging that. So we're going to be making this substitution several times over the next few minutes. When we see a V2, we can get it in terms of V1 and the axial induction factor using this. Now let's just take a look at the limits of the axial induction factor. If the axial induction factor is 0, just going back to our equation here, if the axial induction factor is 0, it means V2 equals V1. Okay, so that's one limit. Axial induction factor of 0 means there's no change in velocity as the air approaches the wind turbine. The other extreme is an axial induction factor of 1, which means that V2 is 0. And again, if we go back to our equation here, if the axial induction factor is 1, V2 equals 0. 1 minus 1 is 0. So these are the limits of axial induction factor. 0 to 1. So it's a normalized velocity difference. 0, no change in velocity. 1, the velocity at 2 has been reduced all the way down to 0. So we want to keep those limits in mind because we'll be revisiting them later. Now, the next conservation law that we want to apply is conservation of energy. And remember, we have 4 locations along here, 1, 2, 3, 4. So the very first segment of our control volume that we're going to apply conservation of energy to is from 1 to 2. So that's from the free stream, a long ways in front the undisturbed free stream, to just in front of the rotor plane. So if you recall the assumptions we made at the beginning, we can apply Bernoulli's equation. Bernoulli's equation is conservation of energy. We're applying it to a frictionless flow. So these are the terms that are going to be left in conservation of energy or in Bernoulli's equation. Notice I don't have any elevation change here. This is just horizontal flow approaching our wind turbine. So there's no Z term. So P1 plus rho V1 squared over 2 has to equal P2 plus rho V2 squared over 2. Notice this form of Bernoulli's equation, there can't be any work transfer. But from 1 to 2, there's no shaft work. Okay, that happens from 2 to 3. So we couldn't apply this from 2 to 3, but we can apply it from 1 to 2. So this is starting to relate the free stream conditions to what's happening immediately in front of the rotor plane. So just rearranging this, we want to get an expression for P1. So P1 is P2 plus rho over 2 V2 squared minus V1 squared. All I've done is taken that term over to the other side. We want to do that because we're going to combine this very soon with a very similar equation from 3 to 4. So we'll just set that aside for a moment. So here's where we do Bernoulli's equation from 3 to 4. So notice we've jumped across the rotor plane here now, going from immediately downstream of the rotor plane to location 4, which is the exit of our control volume. And so P3 plus rho V3 squared over 2 equals P4 plus rho V4 squared over 2. Again, there's no shaft work or anything from 3 to 4, and it's a frictionless flow, no elevation change. So Bernoulli's equation relates pressure and velocity between those two locations. So I'm going to rearrange this equation as well and solve for P4. So I'm essentially just taking this over to the other side. So that'll be P3 plus rho over 2 V3 squared minus V4 squared. So we've applied Bernoulli's equation from 1 to 2 and also from 3 to 4. Now I want to connect these two equations together. The reason that I've isolated P4 by itself on one side of the equation here, and I isolated P1 by itself on one side of the equation previously, is that those two pressures are the same. Both P1 and P4 are atmospheric pressure. Now, let me explain that. So we're choosing location 1 far enough upstream of this wind turbine that the effect of the wind turbine hasn't been felt yet. Those are called the free stream conditions. So we have atmospheric pressure there. Now, we're also making sure location 4 is far enough downstream that the pressure has returned to atmospheric pressure. So there's certainly a disturbance in the pressure as the air flows over top of the turbine blades, but location 4 is far enough downstream that that pressure difference is gone. So both P1 and P4 are at atmospheric pressure. So that means I can take this side of this equation and equate it to that side of the previous equation. So when I do that, I get this. So P2 plus rho over 2 V2 squared minus V1 squared equals P3 plus rho over 2 V3 squared minus V4 squared. So we're starting to relate properties in front of the turbine to properties behind the turbine. Remember, we also said earlier when we were looking at conservation of mass that V2 is equal to V3. There's no change in area, therefore there's no change in velocity. So we can get rid of a couple of terms here. V2 and V3 cancel each other out because they're equal. So what we have left is the pressure difference, P2 minus P3. So remember, that's the pressure immediately in front of the rotor plane. That's the pressure immediately behind the rotor plane. So that pressure difference is related to this difference in squares of these velocities. So notice these are immediately in front and behind the rotor plane, but these are a long ways in front and a long ways behind. But it's relating a pressure change to a kinetic energy change. Now we want to take a look at our momentum equation. So notice we've brought in conservation of mass. We've brought in conservation of energy in the form of Bernoulli's equation. Now we also want to apply the linear momentum equation. And we're going to apply it all the way from 1 to 4. So that's our complete control volume. Well, I'm not starting with the completely general equation here. We've done that many times. But if we were to do that, we would find there would be 3 terms remaining. The left-hand side, the reaction force is the only term that wouldn't cancel out. So that's the force in any solid object cut by our control surface. And then on the right-hand side, we'd have a single exit, m dot times v4, and a single inlet, m dot times v1. So the reaction force is the mass flow rate times the change in velocity. Well, where's this reaction force in this application? Well, it's the tower. Our control surface cuts through the tower holding the wind turbine in place. So that reaction force is balanced by the mass flow rate and the change in velocity that the air experiences. Now we can also apply the linear momentum equation from 2 to 3. And remember, that's immediately in front of the wind turbine to immediately behind the wind turbine. So that control surface also cuts through the tower. So on the left-hand side, we also have the reaction force. Now, because the mass flow rate is the same at 2 and 3, and the velocity is the same at 2 and 3, these inlet and exit terms that were important here go to 0. However, the pressure force is not 0 for going from 2 to 3 because the pressure at 2 and the pressure at 3 is different. So what's left of the linear momentum equation for this control volume from 2 to 3 is the reaction force and a pressure force. Remember, this was originally on this side of the equation in the pressure integral. But this same reaction force here can be equated to area times pressure difference and also mass flow rate times velocity difference. Now notice this area here, that's A2 and A3. I've dropped the subscript on it because that's actually the area of the rotor. So that's a very important characteristic of the rotor. So linear momentum equation applied twice yields these two results. So we can equate these because those reaction forces are the same thing. And this momentum change then is equal to the area times this pressure change. So this is what the momentum equation tells us about the pressure difference and the velocity change. Now next, we're substituting in for this pressure change the result we got from Bernoulli's equation. So no change on the left-hand side except I've changed the sign. And therefore this is changed to P2 minus P3, and the result we have from Bernoulli's equation for P2 minus P3 is this: A times rho over 2 V1 squared minus V4 squared. Now the next thing we would like to do with this is get rid of this mass flow rate, or at least get it in terms of the other parameters that are already in this equation. So mass flow rate is density times the area of the rotor. Notice I don't have a subscript on here, so that's the area of the rotor, times V2. So that's the mass flow rate evaluated right immediately in front of the rotor plane. Well, this V2 we can write in terms of our axial induction factor as V1 times 1 minus A. So we want to get this axial induction factor into this equation because it's a very important parameter, as we'll see, governing the performance of this thing. So this is just substituting this in for mass flow rate. So we have all of that for mass flow rate. So that's our mass flow rate. Still have V1 minus 4 here. Now the right-hand side, A rho over 2 hasn't changed, but we've expanded this out using a difference of squares. So that's equal to V1 minus V4 times V1 plus V4. And the reason we did that is we can see there's several things cancel on the two sides of this equation. There's density on both sides. There's area on both sides. So that's another reason why we got rid of this mass flow rate and got it in terms of density, area, and velocity, is we can simplify this equation greatly by doing that. The other thing that's on both sides of this equation is the V1 minus V4. So that can also be canceled out. And what we have left is 2V1, so that 2 is coming from over here, just bringing it up to the other side, 2v1 times 1 minus a equals v1 plus v4. So a fairly compact relationship, but what is this going to do for us? Well, it's telling us some very important things about v1 and v4 that I want to talk about. So v4, I'm just rearranging this equation and solving for v4. So I'm just distributing this in here, 2v1 minus 2av1, and then moving this v1 over the other side. Okay? And then, of course, there's 2v1 there and a v1 there, so that just becomes v1. So we can see that v4 is v1 times 1 minus 2a. So remember, when we defined the axial induction factor, it told us something about v2 relative to v1. Now we've looked at these conservation laws, and they're telling us something about v4 relative to v1. And they're telling us something interesting. So here's what we got for v2. So v4 equals v1, 1 minus 2a, fine. v2 is v1, 1 minus a. So notice what this means. It means that the speed reduction that the air experiences as it interacts with the rotor, half of it occurs in front of the rotor, because that gets us to v2, and the other half occurs downstream of the rotor. So v4, remember, is our final velocity, leaving our control volume at the extreme right edge. So that's v1, 1 minus 2a, so twice as much of a reduction as right at the rotor plane. So half the speed reduction occurs in front of the rotor, and half occurs behind the rotor. So this is a little bit counterintuitive. It's probably easy for you to see that as the air approaches the rotor plane, it's going to slow down. It's seeing an obstruction there, or a partial obstruction, so it's going to slow down as it approaches that. But it's probably a little bit counterintuitive to understand why, after the air passes through the rotor plane and is heading downstream, why does it continue to slow down? What is causing that reduction, further reduction in velocity that we're seeing here? v4 is slowing down more than v2. So I want to talk about that and see why that is. And in order to do that, we want to plot two quantities as a function of axial position. So this is the axial direction x. And you'll remember there's four important locations: a long ways upstream, immediately in front and immediately behind the rotor plane, and then a long ways downstream. And the two quantities that we want to plot on the vertical axis here are pressure and velocity. So the first one is velocity. So we know we have some free stream velocity back here, v1. And as the air approaches the rotor plane, it's slowing down. So it's dropping, dropping, dropping. And in this illustration, I've got it dropping down to here. So v2 is this value. So our axial induction factor here is the change in velocity. So from there down to here, divided by this velocity. So it's relatively small, maybe 10% or so, 0.1 for an axial induction factor. But the key thing is the velocity is decreasing. So that's fine. So the velocity decreases as it approaches the rotor plane. Now we applied Bernoulli's equation from 1 to 2, and that tells us that as that reduction in velocity is happening, there will be a corresponding increase in pressure. Now, this dotted line is a reference pressure. That's atmospheric pressure. So a long ways upstream here at location 1, the pressure is equal to atmosphere. But as we approach the rotor plane, velocity decreases. Therefore, Bernoulli's equation says the pressure increases. So the pressure immediately in front of the rotor plane is going to be something higher than atmospheric pressure. So decrease in velocity, increase in pressure. Now, as the air passes through the rotor plane, however, there is a pressure drop. So this thick line that is shown up here is meant to show that. So we've passed through the rotor plane, the pressure drops down. So there's an obstruction there, air flowing through it, decrease in pressure. But remember, the velocity doesn't change. So V2 equals V3, but there's been this drop in pressure. Downstream of the rotor plane, the pressure is going to recover back up to atmospheric pressure. So it's below atmospheric pressure here, but as it heads downstream, its pressure is going to recover so that when it gets to 4, it's back to free stream pressure, back to atmospheric pressure. Well, if we take a look at what happens to velocity, now that we're through the rotor plane, we can again apply Bernoulli's equation. We can't apply it from this side to this side, but we can, and we already have, applied Bernoulli's equation from this side downstream. So from 3 to 4 we can apply it, and what it told us, or what it tells us, is that if the pressure is increasing, the velocity has to be decreasing. Conservation of energy. So that means this pressure recovery that we see in the wake of the wind turbine causes a further decrease in velocity. So the velocity ends up dropping in front of the rotor plane and behind the rotor plane. And in fact, the analysis we just did tells us that the amount that it reduces in front is the same as the amount that it reduces behind. So this velocity here is halfway between this one and this one. So that's an important thing to understand about fundamental operation of these types of machines. Now we're going to apply conservation of energy one more time, but we're going to apply it all the way from 1 to 4, so the entire control volume. Well, we can't use Bernoulli's equation there because we have a work transfer, so we would have to go back and use our more general conservation equation. But if we did that, this is what would result. We would have shaft work, because there's now a shaft penetrating our control volume, so we have shaft work being extracted, and we have kinetic energy entering and leaving our control volume. So that's what this equation amounts to. The change in kinetic energy of the fluid, so V squared over 2 at the inlet, V squared over 2 at the exit, that's the kinetic energy per unit mass that the air possesses. Multiply that by the mass flow rate, and we get power. So the shaft power equals mass flow rate times V1 squared over 2 minus V4 squared over 2. Total change in kinetic energy. Now, all of this entire analysis we've been doing because we're interested in this quantity. So everything that we've done so far is to try figure out what is this shaft power. So let's take a look at the right-hand side of this equation and see if we can figure that out. Well, we already have some results that are going to help us with this. We're going to do the same thing to this mass flow rate as we did to mass flow rate recently. We're going to represent it by density times the area of the rotor times V2. But we're going to write V2 as V1 times 1 minus the induction factor. So this is rho A V2. The 1/2 here has been factored out. V1 squared we leave, but V4 we're going to replace with V1 times 1 minus 2A. But we need to remember it's squared here, so all that stuff gets squared. So we're using our result that we just got for V4 and putting it in there. So this is the power coming out. Now you'll notice that axial induction factor plays a very important role in here. Now we can simplify this a little bit, gather up some terms and simplify it, and that's what we're going to do. So we have a V1 here and V squareds here, so factor these out and you get V1 cubed, very important term that I'll talk about in a little while. These two 1's cancel each other and we factor out a 4, so the 4 in this 2 becomes this 2, and so we just have an A minus A squared left in here. And we can factor an A out of this, and that will become 2 rho A V1 cubed, A times 1 minus A squared. So remember what this is. This is the power that this thing is going to produce. Obviously we're interested in that. The density of the air, the area of the rotor, the velocity of the air coming towards it. So all of those are just operating conditions, right? Density of the air, not much we can do about that. The area, well, that is determined by how big a wind turbine we're talking about. The velocity, how windy is it today? So all of those things are geometric or operating parameters. The only one left on the side that is really a performance parameter of the particular wind turbine is this axial induction factor. Now it occurs in a couple spots, but that's no problem. So that shows that axial induction factor is obviously going to play a very important role in how much power this thing produces. And that kind of stands to reason. Axial induction factor tells us how much the air is slowing down. Presumably, the more it slows down, the more power will be produced. However, it's not quite that simple. Now, what we want to define here is a dimensionless power, and that's called a power coefficient, and CP is the symbol usually used for that. So in the wind turbine industry, the efficiency of a wind turbine is called the power coefficient, and CP is used for that. So how is CP defined? Well, it's an efficiency, so it's defined as the actual power produced, which we have an expression for, divided by the total kinetic energy in the wind. And that is 1/2 rho AV cubed. So the kinetic energy per unit mass is 1/2 V squared, but the mass flow rate is rho A times the other V. So this is the total kinetic energy available in the wind. And this is the amount that we're successful in extracting. So the ratio of those two is the efficiency of the wind turbine, called the power coefficient. So we're going to just substitute the expression we have for shaft work into that. So we get this, and you'll notice that lots of things cancel here. We can reduce this down quite quickly. The area is in both, the density is in both, V1 cubed is in both, the 1/2 comes up and becomes 4. So this shows the central role that the axial induction factor plays in determining the efficiency. The efficiency is essentially depends on that axial induction factor. Now, we want to explore what this relationship looks like. So we can easily plot CP as a function of A, and that plot looks like this. So CP versus axial induction factor. Just took the equation on the previous slide and plotted it. Well, there's lots of interesting things here. First of all, we notice that CP is 0 if A is 0. Now remember the physical meaning of A. If the axial induction factor is 0, it means V2, the velocity of the wind at the rotor plane, is the same as V1. In other words, it hasn't slowed down at all. And also V4 is the same as V1. So this condition here would happen if the blades essentially didn't extract any power from the wind. Let's say they weren't even turning, or there weren't even blades mounted on it. The wind is just blown by, doesn't even notice the thing is there, no change in velocity at all, therefore no power produced. Okay, so that's that limit. The other extreme right here is an A of 1. So that's an A of 0, this is an A of 1. And if we look into our equation, just peek back at the equation, we see an A of 1 is also going to cause the CP to be 0. So why is that? What does an A of 1 mean? So the velocity reduces as it approaches the rotor plane, and it actually comes to a stop, or it comes to rest in front of the rotor plane. So this is what would happen. Let's say the rotor plane, instead of being blades that are rotating, is just a great big solid disc. No flow through the rotor plane at all, because V2 is 0. So the mass flow rate through the rotor plane is 0, so there's no opportunity to extract any energy. So this extreme also doesn't produce any energy. So in between those, there is energy production, and CP is bigger than 0. So the other point that we're obviously interested in is right here. What does the axial induction factor have to be to give us that maximum value of CP? That's what we want to know. Now, we can find that out. So, we know that at this location, dCp by dA, in other words, the slope of that line, has to be equal to 0. Well, we know that Cp is related to A by that, so we can differentiate this, and if we do that, we get 4 1 minus A squared plus A to A times 1 minus A multiplied by minus 1, derivative of the minus A inside here. So just working with this and solving for A to find out what the value of A is right there. So that gives us 1 minus A squared equals 2A times 1 minus A. Divide both sides by 1 minus A, and we quickly find out that the optimum value of the axial induction factor is 1/3. So this value of A is 1/3. So a very important result. We want to design the wind turbine, so when we're going into the detailed design of the blades, we want to do it in such a way that that axial induction factor is as close to 1/3 as possible, because that's when we'll get maximum power output. Now, we're also interested in figuring out what this is. We've figured out the optimum axial induction factor. Well, what is the maximum efficiency? Because that's also of interest here. So we'll take a look at that as well. So back to our CP relationship, we know that A is 1/3, so we can just substitute a 1/3 in there and in there. So we'll now be finding CP max, this value here. So just putting 1/3 in there and solving this, it comes out to 16/27. So that is the maximum possible CP, or the maximum possible efficiency of a wind turbine, and that is known as Betz's limit. So it's impossible for the efficiency to be any bigger than that. 16/27 is 59.3%. So that's the maximum possible efficiency.